that I have down on the bottom, the little toolbar, does Zoom show you that too? Or does it show you just the PowerPoint screen?
Just the PowerPoint screen.
Sweet, because I hate having the controls over your faces. And so if it doesn't show it, then I'm totally keeping it over there. Win. All right. So the question we started with, so make sure first you have your Unit 7 notes out. So everybody check right now. Go look, Unit 7 notes. Take a second. Check. All right. Reference packet. You always need it. So make sure you have that. Check. You need a calculator. If you're going to use Desmos, have it open in a tab because we are doing the maths thing today for the first part. Check. And then all of the questions we are covering today are also shown to you on Warm-Up 7.2 under the optional resources where you see little textbook emojis. So that Warm-Up 7.2 PDF is there. So if you are forgetting what I'm saying or want your own copy to work off of, or if you're super whammadine and can write on your screen, you can follow along, okay? Although all of that's not necessary, I do expect you to be working these on a piece of paper or a whiteboard or something so you can have practice. So our warm-up question, we will start. I have my wheel on the phone because they made an app for my wheel, which is super exciting in a way that y'all don't care about, and I am like stoked. It's less tabs. I have to have my computer look at that madness. It's awesome. Okay. All right. Shanmati, you're first up. What do we have to do before we start any question ever in any subject anywhere?
You have to read it.
We have to read it and know what piece of information?
What we're finding and what we're given.
Yeah, what we're finding and what we're given, right? So this question says, how many liters of carbon dioxide are produced if 2.98 moles of methane are burned? So you tell me, what is this question asking me for?
Liters of carbon dioxide.
Perfect. You said it with such like, you have a really great like flight attendant voice. It's very calm and soothing. So, you know, like it's very nice in case you didn't know. Maybe it's all the Zoom practice, right? So liters of CO2 is what the question is asking us for. So if we get to the end of the question and we don't have liters of CO2, we are not answering the correct question. What information do you think is important here?
2.98 moles of methane.
Yep, so written things are always important. What else is important? What else tells you something that if you are a chemistry person, you know what that means chemically. And if you're not a chemistry person, you may not know what that means chemically.
Burned.
Burned. Burned is important. Why is burned so important?
That lets us know which formula we're writing, so it would be combustion.
Yes, it tells us our reaction type, which is how we can predict the reaction. 10 out of 10, gold stars for you. Thank you so much. That was fantastic. Loved it. All right. So, Sangeet, what would you do next? What do you think?
I would write a formula.
A formula for what?
The combustion, and you're using methane.
Oh, you're the first person to get it today. Give yourself a round of applause. It was fabulous. You're the first one to get it. Most people have gone straight to the math and then they realize they need the reaction and go backwards, but you remembered reaction first. Remember, last class, what I gave you was the reaction that was balanced. So the only difference between today and last class is we have to create the reaction and balance it. So you did awesome. Tell me how you would start.
So methane is CH4
How do you know that?
because of the prefix.
The prefix, and if you don't remember your prefixes, what piece of paper stapled together can help you?
Reference packet.
The reference packet. Oh, it's clutch. That's going to be the MVP of the year, right? Reference packet. So methane, you could look up how to name that in the reference packet. Awesome. I'm going to move on to someone else now because I've tortured you for a very long time and you've handled it very well. Dia, what do I do now? I know I have methane. I converted it. That's great. What do I do now?
You make it into a combustion reaction.
So how do I do that? You are absolutely correct. How do I do that?
I forgot.
That's okay. Let me ask you this. What's required for things to burn? Why do we blow on a fire? Like that, make it bigger. What are you providing to that fire to make it bigger?
Oxygen.
Beautiful. Yes, we have to have oxygen. So one of our reactants must be oxygen. How do I write oxygen in a chemical reaction?
O2.
Lovely. Why is it O2? Not just O.
Because it's diatomic.
It's diatomic. Okay, everybody. What are the diatomic elements? What was the phrase I taught you? Anyone remember? Go ahead and hit the space bar if you do.
Have no fear of ice cold beer.
Once you're 21 or if your parents give it to you. You have to add that to it so I don't get in trouble, right? So have no fear of ice cold beer. HNOF. Wait, have no. HNFOCl and Br. Yep. Okay. So, yep. Burned is combustion. Yes. Good. I think I just got a direct message late. It just popped up. So I'm pretty sure that you put that earlier, but that's okay. You were correct. Yes. So methane plus oxygen, and I wrote methane here so you guys knew where I got that CH4 from. You do not need to write the word above things normally. Okay. So we have CH4 plus O2 because it's one of our diatomic elements. I'm going to torture someone else now. Good job, Dia. Darshan, you're up, dude. What are my products? If these are my reactants, what are my products?
Carbon dioxide and water.
Good. Always carbon dioxide and water. Remember, water initially changes into a liquid, but there's so much heat in the process, it instantly vaporizes into a gas, which is why you never see water at a combustion site unless it's a super huge combustion or something. And even then, no, because I will talk about that after class. If you guys are interested in how space rockets work, my brain is totally off track. That's okay. I corrected it and I got myself back on track. See how that works? Adults can do it too. All right. So thank you, Darshan. So what do I need to do now? Izzy, what do I do now? I have my reaction. What do I need to check?
Balance it.
Ooh, yes, I need to balance it. I need to balance it. So how do I balance it? What do we do with combustion reactions?
So I first looked at hydrogen. So I put a 2 in the H2O, like in front of the.
Let me reverse on you a little bit because you are jumping ahead and you did wonderful things in your head, but just in case someone else is confused, can you tell me how much each thing on each side to start with?
Oh, yeah. There's 4 hydrogen on the reactant side
Okay.
and 2 on the product side.
Okay.
And then there's 1 carbon on the reactant side and 1 on the product side.
Yep. So there's 1 and 1. And then how many
And
oxygen?
then 2 oxygen on the reactant side and 3 on the product side.
So in your head, I'm going to guess you really started with carbon, but you saw carbon was equal. So you moved to hydrogen. Because we talked last class about CHOing on combustion, right? CHO. So that's why I said you did a bunch of things in your head really fast. And I see you, girl. That was awesome. I just wanted to back up a little bit in case someone else didn't track that fast. But you did awesome. So let's keep going. So what did you do next? Sorry.
Okay. So after looking at carbon and that was fine, I put like a coefficient of 2 in front of H2O on the product side in order to have the hydrogens match. And then, so that made hydrogens match. And then oxygen became 4 on that side.
Okay.
So on the reactant side, I put a coefficient of 2 in front of O2.
Yep. And now everything is balanced. Yes. So Sneha, yes. So the reminder is we do carbon first, then hydrogens, then oxygens. The reason we do oxygens last is that oxygen is the only thing by itself. So if we balance everything else and then we end up with an odd number on the right, we know we have a crazy Aunt Karen where we have to double everything. If you go through all of it like this one and oxygen ends up even, because sometimes it does, because again, combustion is like, it's fickle, right? It's weird, it changes. And it goes evenly, then we don't have to double everything. So we always do CHO. So instead of chewing on it and thinking on it, we CHO on it, right? So CHO, always do it in that order, CHO. That's also how it will always be written. If you notice the C comes first, the H, and then the O. So just go in order. And it'll come out easier for you each time. Scale of 1 to 10, how we're tracking so far. Okay, so guys, That is literally the only difference. Doing this process at this point, everything is now the exact same as what you did last class when you did the drag and drops. We're just not dragging and dropping. So this is the only new part. And when I say new, it's really, really old. And we took it and we strung it together, right? So again, this is a bunch of concepts. We have been building up to this for a whole semester. 80% of what you've learned is because we need to do stoichiometry. So like, you guys have been building up, and I know it feels kind of anticlimactic. It's like when a movie builds up really big and you're like, oh man, that wasn't that bad. It's not that bad because you guys are awesome and you're listening and you're practicing and it's great, okay? All right, so I'm gonna erase the balancing part of this so that way I can focus on the next steps. But just know, I write that balancing out every time instead of doing it in my head so that if you are confused, you can see where my brain went because I am a teacher. You do not need to write everything every time you do it if you can do it in your head. Just be confident when you do it, okay? My job is to show all the steps, but if you are super whammadine, high speed, low drag math person and you can do some stuff in your head, that's cool too. All right, so now we've reached that point. It's the same as last class. So next person, you're gonna take me through what is step one. Faisal, what's step one?
So the first thing I did was for the train tracks, I put 2.98 moles of methane or CH4 on the top.
Yes, and I love, super am in love with the fact that you said 2.98 and moles and methane and CH4. Super whammadine, hit it out of the park. You did fantastic. Love it. Thank you so much for remembering that. Okay. So what is step one of stoichiometry? Now that I wrote it in, what's the first thing I'm supposed to do? For any problem. Remember the 3 steps I taught you guys. Sorry, I forgot to click the wheel. I'm like staring at you and I didn't say a name, did I? That's on me. Victoria C. Victoria C, are you here today? No. Victoria V then. I'm just gonna go to the other Victoria because it says Victoria. What's step one?
I forgot.
That's okay. Does anyone remember? I made you guys say it a bunch of times. Do you remember? Anybody? Yeah, convert to moles. I see a bunch of people hitting the chat up. Convert to moles. So what's step one?
Convert to moles.
What's step one?
Convert to moles.
And after you balance your reaction, what's the first thing you do?
Convert your moles.
Yes, you convert to moles because moles are the bridge. The moles allow us to relate one element to another because everything happens on an atom to atom basis. It's a really fancy word you learn in IB called molecularity, which I think is really funny sounding and it's really fun to say. You know how sometimes words are fun to say? Molecularity is one of those really fun words. And that's what it's called. It's everything happens on a molecule to molecule basis, okay? So if we know how many molecules we have or how many moles we have, because that's the one that we can convert from one to the other, then we can look at everything in equivalency and compare one to another. Okay, so we're going to convert to moles. Step one, convert to moles. I'm going to write it out here for you. So that's step one. And step one was convert to moles. And I keep saying that, but it's the most missed step. So is this converted to moles? What do you think, Victoria? Yeah, it was already converted to moles. We don't even have that much to do. Fabulous. Step one was done for us. Fantastic. All right, I'm going to quit picking on you now. Good job. Thank you for putting up with me. All right, so I'm going to put this here. Step two. What is step two? Eden. What's step two?
Because it's already in moles, you have to put moles at the top, so moles at the bottom for CH4.
Yes, and what you're describing is called comparing moles or a mole ratio. So whichever one sticks in your head, sometimes when I say mole ratio, kids go, ooh, because it's a math word, but you're just comparing moles of one to moles of the other. That's all that means. So step one, convert to moles. Step two, compare moles. And you correctly identified that the moles of CH4 would need to be on the bottom because that is what we have on the top. If we put it on the top, units math, just like numbers math, and you end up with mole squared, methane squared, which would be weird because we don't square things when they're units, right? Well, at least right now. So mole squared, methane squared, not a thing. We put it on the bottom. What goes on the top?
Moles of CO2.
How'd you know to pick CO2? There are 3 different elements there. It could have been oxygen or water or CO2. Why did you pick CO2?
Because we're trying to find the liters of carbon dioxide, so it would make the most sense for there to be CO2 at the top.
Yes, our question is asking about CO2. So even though it's not moles of CO2, that's the one we pick. And how many moles of each one do we have? There's nothing written here. So what does that mean?
1 of each.
Those mean 1 each. You don't normally need to write them, but I'm going to write them here. Awesome. Thank you so much, Eden. Next person, Kai. Step 1 was convert to moles. Step 2 is compare moles. What's step 3?
Converting out of moles and like
Convert
to what
out
you
of
need to
moles.
find.
Yes, we want to convert to what we want. So convert to desired, which is the question, right? You could write the question, convert to answer, whatever it is, but it's the units we need in our answer. So that's what this is. So what do we need to convert to? I think you said it.
Liters.
Yes, liters. So would liters go on the top or the bottom?
Liters would go on the bottom.
So if I put liters on the bottom, I'm going to end up with a unit of moles squared over liters. Is that what I want?
No.
So here my unit is liters. It is not 1 over liters. So if liters is on
Okay.
top in my answer or on top in what I'm asking, it has to be in the top at the end. So this is asking for liters of what?
Carbon dioxide.
Okay, so what do I put on the bottom? What am I trying to cancel?
You're trying to cancel the moles.
Okay, so now magic question, what numbers do I put here? What values?
Would you actually? I'm not sure.
That's okay. What usually helps us when we need a number that's a known value? Where do we look?
The reference packet.
Go to page 2 or the back
Mhm.
of the title page if you have it printed. Okay. And then you go to constants and conversions, and it's either 6 or 7 down. You'll see volume of gas at STB. So what does that give you? What conversion factor?
22.4 liters is equal to 1 mole.
Yep. And if it's not given, assume it's a STP. So 22.4 liters for every 1 mole. So that 22.4 is stuck to the liters and the 1 is stuck to the mole. Awesome. Thank you, Kai. You did a great job. And thank you for reminding us about the reference packet. Okay. So Jessica, what do I do now? Before I start putting it in my calculator, what can I do?
With like every set of like the fraction looking thing, put parentheses around them so that way you know how to type into a calculator.
Yep, pretend it's parentheses. We can also unit check. So if we cross off everything that's on opposite sides, the only thing we should have left is an L and a CO2. Everything else should cancel out. And if that is true, the only way you can get this wrong is by putting it in your calculator wrong. These calculators are stupid. They don't know what you mean. So moles of CH4 cancels with moles of CH4. Moles of CO2 cancel with moles of CO2. I'm left with liters of CO2. I know my math is right. So now I'm putting it in my calculator just as I see it. So it's 2.98, 1 over 1, and 22.4 over 1. Now, the next comment I usually get in the chat is, Miss Longley, 1 over 1 is 1. You don't have to type that. I fully understand, but even at my master's level, I have a habit of always doing things the same way so I don't mess something up. For example, I was doing something off of memory and I misread 1 over 24 as 22.4 over 1. And then I messed up the whole problem because I just said, oh, I only have to try to type 22.4, and I tried to do something in my head. But if I've trained myself to type exactly as it's written, then you won't make mistakes. And again, remember that I'm giving you the jump button. So if I'm giving you a habit now, this is a habit I wish I would have had when I got into upper levels, right? These are habits I had to teach myself because I didn't have a teacher going, hey, this is going to get more complicated. Please do it now like this. Now there's a reason. And I just ignored all of them because I'm like, I can do this my way, whatever, I don't care. And I had a chip on my shoulder that was about the size of Kansas. So it was a problem. Anyway, so now we have this. What did you get in your calculator when you put that in your calculator? You are not in here right now. Ray, what do you get out of your calculator?
Give me a sec. I'm putting in the calculator right now.
Okay, no problem. I will wait.
66.752.
66.752. So sweet, I'm done. Question done. Super
It's
done.
not sig figs. My bad.
Not sig figs. I'm just being facetious. I do this every time, right? So sig figs. How do I do sig figs? What do I do there?
It's 66.8.
Okay, so how did you decide 3 sig figs? Because there's a question in the chat that I got that I'm going to address at this point. How do I tell how many sig figs?
It's the least number in the multiplication, so it'd be 3.
Yes, so we're given a number with 3 sig figs. So remember, it's only measured numbers. Exact numbers do not count, right? So 2.98, that is a measured number, so that counts. This conversion, does it count towards your sig figs?
Oh yeah, it doesn't.
It does not count because these are exact numbers, because this is an exact relationship of an exact count. So this is not measured, okay? What about this guy?
Only the top one?
So this is the question that I got. 22.4 and 6.022 times 1023 are exact numbers. So this is an exact relationship, but it is inherently measured. It is debatable whether it is included or not. The way Mr. Harridan has taught you is not to include it, and that is the way half of my professors had it. The other half of my professors said 22.4 technically by the nature of the number has to be measured, and therefore blah, 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 blah. So I'm gonna say for this, I like to tell you that to say, even in science, people disagree, right? So I'm going to say count it as an exact number for right now, because we'll say conversions are exact numbers. But no, if you go to college or if you come to IB or AP, they may require you, because AP and IB also are not in agreement on this. Depending on which one you do, they may tell you something different. So just know in your head, this is something you need to define with your professor if you move on. Okay?
Okay.
That makes
Thank
sense. No problem. I know that was not your question. There was multiple questions about it in the chat. So I used your question that I asked you to springboard and answer the other one. So you did a good job. So 3 sig figs, I count 1, 2, 3, draw the wall, come back. So that gives me 66.8. So I'm done. I'm super done. All the way done. No? What did I forget?
You need to add the liters of carbon dioxide.
The liters, and what else do I need to add?
Carbon dioxide, CO2.
So you need to add units and molecule, right? Otherwise, our number is not fully dressed. It's like, if you don't put the molecule, it's like not putting on your pants when you come to school. Like, you got to put your pants on. Units are the shirt, molecule are your pants, put your shirt and your pants on. Don't be in a pro, okay? Are there any questions on this? This is 7.2. Again, this is review, the half part. So everything, up. Oh, come on, stop. My Wacom tablet decided to be weird. Okay, so this is the same as last class. This is the only thing we added. So this is what you practiced all last class, this stoichiometry part. This is the only thing we added, okay? That is what you're required to do for 7.1, which is due tonight. Scale of 1 to 10, how do we feel? Okay, love all the responses. We're going to shift gears away from math and into our minds. So you can put the calculator away. You won't need the reference packet for this portion, most likely. You should not need it for this portion. Oh wait, you might need the naming flow chart. So yes, keep the reference packet out, but you will not need your calculator. We're going to shift and we're going to do a little bit of stuff in breakout rooms, just a little bit for short periods of time that are timed, and you're going to come back. So if you have not pulled up warm up 7.2, again, all of these questions are in warm up 7.2. What I want you guys to explain in breakout rooms, I want you to explain why water and oil do not mix. I'm going to be giving you around 3 people per room. Okay. And you are going to be discussing this. You need to have a very detailed answer. Just saying they don't mix is not a thing. Okay, that's like defining the word in the question. You have to tell me why chemically and make sure you include the word polarity. Again, this is in your reference packet, or not your reference packet, your warm up 7.2. You're going to have 2 minutes to discuss. 2 minutes. Okay, rooms are open. Go do the thing. I was reading one of your guys' emails about it not rounding correctly on 7.1, which I know is a thing. So in case you were the person I just responded to, because they're in here, I'm going to look at 7.1 to see how the rounding worked. And just like I did with QC 4 point whatever last semester, since I programmed it to have a margin of error of 0.5, but it doesn't seem to have done that. So I'm going to go back and look at the programming and see if I can fix it with the adjustment to the programming. But if not, I will go hand grade them. I'm hoping I don't have to, but we'll see. So sorry, I was totally reading that and involved. So, Madison Wong, why do water and oil not mix?
Because oil is non-polar and water is polar, and you can look at like when you write it out, there's stronger pulls towards one side, which creates a partially positive end and a partially negative end.
Yep. Asymmetrical.
Whereas for oil, it's symmetrical.
Yep. So for water, it's asymmetrical shape and or behavior because it's the H, it's the O, and it's the H. And just like you said, the oxygen or the electrons are pulled toward, that's supposed to be 2. Electrons are pulled towards the oxygen, which gives it partial negative and partial positive. Oils are hydrocarbons, so they look like weird versions like this. I'm just going to pretend H's aren't all those. So they're all symmetrical and therefore it's nonpolar. The rule is like dissolves like. So polar things dissolve polar things, nonpolar things dissolve nonpolar things. They do not mix otherwise. That was picture perfect. Thank you so much. Sorry for my short delay. I feel bad. All right. Next, we're going to look at what that looks like in actual molecules. So Akshar, okay, this is sucrose. We need to know if it dissolves in water or oil. What do we have to determine about that compound before we determine if it'll dissolve in water or oil?
Is it polar or non-polar?
Is it polar or non-polar? So what do you think?
It's polar.
How do you know it's polar?
I just guessed.
Okay, so one, we know table sugar dissolves, right? We've all had Kool-Aid and Gatorade and sugar water and things that if you've taken a Kool-Aid packet and put it in water and drank it, you've dissolved sugar, right? Sugar dissolves in water. That's something we know. The reason it's polar is because it's asymmetrical in shape and behavior. See how this is like knobbly looking and it's not symmetrical? That's one thing. So asymmetrical shapes. But also take a look at the charges. So these are the partial positives and negatives. These negatives are clumped together. Over here, there's a positive negative. Here, they're farther apart. Here, there's 2 positives really far apart. So this is not symmetrical in the way the charges are distributed at all. So therefore, it's polar because it's asymmetrical in behavior. Scale of 1 to 10, because that's a weird one. So it dissolves in water because it's polar. Okay. Next, benzene. Audrey, walk me through benzene. Are you here, Audrey? Nope, not here today. Oh, that's right. You told me you weren't going to be here today. I'm not even talking to you because you're not here. I was told. Sonali. Benzene. What do you think? Are you not here either?
I'm here.
Oh, awesome. So benzene, what do you think?
Is it non-polar?
It is non-polar. How did you know?
Well, I mean, you just said that like the sucrose is like very like it has a bunch of different charges and like looks like a blob kind of, but the benzene looks more organized, I guess.
Organize the word. I'm going to give you a word. I'm going to say symmetrical. If I were to draw a little dotted line and fold it in half, other than the double bonds not lining up, right? The C's are all symmetrical and the H's are all symmetrical. It's like a perfectly symmetrical snowflake. And then the other thing, so it's symmetrical in shape. It's also symmetrical in behavior. Every single thing bonded to the carbons is hydrogen. If there was a random chlorine somewhere, this would have been polar because that one chlorine behaves differently than the other hydrogens. So this is symmetrical in shape and behavior. It's non-polar. So what does it dissolve in, Sonali? Last question.
Oil.
It dissolves in oil because it's non-polar. Awesome. Bob, you're up. Give me octane.
I don't know. I don't think it's symmetrical. Maybe that's just because the orientation of it.
Okay, so this guy would point this direction. This guy would point this direction. Are those equal and opposite?
Yes.
If I were to go from the center here, I would have arrow pointing this way, arrow pointing this way. Are those equal and opposite?
Yes.
Arrow pointing this way, arrow pointing this way, equal and opposite?
Yeah.
What about here?
Also equal and opposite.
So is this nonpolar or polar?
Non-polar.
Because it's symmetrical, right? So
Right.
hydrocarbons are difficult, but this is octane is like a version of fuel like gasoline, which does not mix with water. So octane and other hydrocarbons are symmetrical as long as everything in it is hydrocarbon, which we know it is because it's using the oct and the ane method, which means that it's C8 and then 2N plus 2, right? H18. So that is the case here. So it is nonpolar. So what would it dissolve in?
Oil.
Oil. Perfect. Good job, Bob. That was a very difficult one. You did a great job. Don't beat up on yourself. No one has gotten that one today. So doing good. All right, Trisha. Give me soap or sodium lauryl sulfate. What do you think?
It says it has a nonpolar tail.
So the nonpolar tail, what do you think about that?
That dissolves in oil.
Okay. What else is here?
The water-soluble head.
It also has a water-soluble head. That's weird. So what do you think about that one?
That dissolves in water.
Yep, that dissolves in water. So bonus question to anyone in the class. Good job, Trisha. So this dissolves both. What does that kind of look like from biology? It's not exactly the same, obviously, but what does it kind of look like from biology?
A sperm cell?
Sperm cells do this too. Yes, where it has the head and the tail that behave differently. What else is there? There is something specific that's cell biology. What part of the cell does that look like?
The lipids in the cell membrane.
The lipids in the cell membrane. Remember how they organize? There's no brain saying, or there's no architect going, okay, here's the Lego piece, click this in, this is the way you go. The entire way biochemistry work is by hydrophobic interactions. We are afraid of water and we put ourselves in a water environment, we're gonna glob up a certain way so we protect ourselves from the water. So all of the tails do not like water and they stay together because they don't like water. And then the part of the heads that are water soluble or they do like water stay on the outside. So when you drop them in water, all the tails magically come together. And that's how cell membranes work because they aren't Lego pieces and there's no master architect putting every cell together. It's all hydrophobic interactions. So this concept you're learning is the basis of my entire master's right here. Like that's a lot of it, hydrophobic interactions. So big stuff, even if it doesn't seem big. You guys are doing great. All right. Scale of 1 to 10 so far, how you're doing? Say sperm cells behave that way because there's a part of the gamete right in the head of the sperm cell that needs to interact with the ovum or like the egg of the female, right? So the tail, we do not want that to be water soluble. We want that to not be water soluble so we can propel ourselves towards the ovum or we would never make it, right? And then you need to be able to dissolve the head so that you can actually expose the ovum to the egg and go in there, right? And so there's water soluble and insoluble parts in that whole thing. So that was also good. And it does look like that. So good call. All right. Yes. All right. So now we're going to go next level. We're going to create the molecule. So Carter, you're up, man. What does nitrogen trifluoride, I can say words, nitrogen trifluoride look like as a molecular formula? What compound goes with that name?
Let me find my reference packet.
Yes, I love that answer. It's the best answer ever. Music to my ears.
Would it be trigonal planar?
So that's the shape, and you are really close. We have to draw the LDS. The molecular formula is like the letters, but I love that you went.
Oh,
Yeah. You're good. So the letters and the subscripts, what would it be? We can talk about that in a second. So hold that up. Keep that out. Okay.
and it would be nitrogen 1, which is N, and then fluoride 3, which is F3.
Yep, love it. Okay, so I'm going to come back to you for that shape question. So you hold the phone right there, Carter. Okay, I'm going to go and pick on someone else because I'm going to come back to you in a second. So he told us it's NF3, which is correct because it's a covalent compound. We know that because of the prefix. Kira, how many valence electrons does nitrogen trifluoride have to work with?
That would be,
How do we tell? Talk me through the process of figuring it out.
so nitrogen has 5 valence electrons.
Okay.
And since there's only one of it, that means 1 times 5 is 5.
Okay.
And then fluorine has 7 valence electrons. And since there's 3 of them, 3 times 7, and that's 21. And you just add 5 and 21 for 26.
Love it. So when we get done with our molecule, we have 26 valence electrons. You've done a great job. All right, you already spoke today. I don't know why it didn't take you off. Lucas, what do I do now? What can I do? There's 2 different methods. There's a math method and a drawing method. Which one do you want to do? What do I do now?
How about the drawing method?
Okay, so what did I start drawing?
So first you draw nitrogen.
Good. And then what do I do?
And then, so it would have 3 fluorides coming off of it, right?
Yep. Now here's my question. How do you know which one's the central molecule?
Because this is one of it.
There's one of it, and there's 2 other ways to tell. It's the first thing written, right? So the first thing written usually goes in the center, and it's the one that's the farthest left on the periodic table. Okay, so those are different ways. Okay, so now what do I do?
Now the bond, like, don't you draw the bonds between the nitrogen and fluoride?
Yep, to be a molecule, they have to be bonded. So everything needs at least 1 bond. So that's 6 of my electrons used up. What can I do now?
Now you need so you do 2 dots over n.
Okay. So that gives me 8 around nitrogen. That's beautiful. It's what it wants. Now what do I do?
And then for each fluoride, you do like dots all around them.
Yep. So how many total dots? Why is it doing that? That is so annoying. How many dots total would it be?
6.
6. So each fluorine will get 6. So let's count and see how many that gave us. So that gave me 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. That's exactly what I needed. You did a good job. Thank you, Lucas. All right. So now, Celine, is this molecule polar or non-polar?
It's symmetrical, so that would be
polar. It is polar. Symmetrical or symmetrical?
Asymmetrical?
Yes, asymmetrical. Fluorine on this side, fluorine on this side, fluorine on this side. There's no atom on this side, so it's not distinct, right? This type of work is like a whole, although they're both strong, they're going to be perfect. What about this guy? How would the bipolar?
I can't hear you if you have something.
Okay, yeah, so which side is partially positive for this bond?
The nitrogen?
Yes, nitrogen partially positive, partially. Thank you. Okay. So, you did a good job. So these two, it's like the Hulk pulling on the Hulk, and this is like the Hulk pulling on almost nothing, right? Much weaker. So therefore, this will be partially positive, that'll be partially negative, and this is a polar molecule. So this will dissolve in water, okay? Scale of 1 to 10, how y'all feel? So I'm going to go back to Carter. Carter, what shape would this molecule be? We're going to remind ourselves of this real quick.
Forgot myself that I was muted. It was trigonal planar, right?
You had said trigonal planar, but let's do the ABE together. What is the A part?
It's the nitrogen, and there's just one.
Right. So this is A, and there is one of them, right? And then we don't have to write the one. I'm just making sure that you guys understand where I'm getting things from. What are the B's?
The fluoride, and there's 3.
So, yeah, B stands for bonded atom, and that's B, B, B. That's 3 of them. And then what's this? What's this considered?
The extra electrons.
Yeah, a pair of lone electrons, there's 1 pair of electrons. So it's A, B3E. So what shape is that?
Trigonal pyramidal.
Yeah, trigonal pyramidal. So what that means is that when you draw this, it looks like N, F, 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 right? Solid is going into the page, dots are coming out of the page, and then there's here. So this looks like a pyramid, and that's where the name comes from. Okay, trigonal meaning the triangle base, pyramidal meaning they all come to a point at the top. Okay, just reviewing that since you gave me the opportunity. Now, I want you guys to go to breakout rooms. You are going to be doing carbon tetrachloride together. I'm going to give you 5 minutes to do carbon tetrachloride. I want you to try that together. So you're going to build the molecule, determine if it's polar or non-polar, and all that jazz, just like this. You don't have to do the shape. I just wanted to review the shape since he said it, and it's something that you do need to know. Okay, so breakout rooms, 5 minutes, carbon tetrachloride, and go.
Miss Longley.
Yes.
Charles Cothran is in the waiting room. His Wi-Fi blew up, and he'd like to be
Oh, I
let in.
totally didn't even hear it ding. Okay, hold on. Thank you for telling me. Or we could just leave
You're
them out
welcome.
there and just be like, you're not one of us anymore. I'm just kidding. All right, there we go. Charles, I'm sorry. I didn't mean to leave you. Hold on. I'm gonna put you in a breakout room, okay? They'll tell you what we're doing.
All right.
I'll put you in this one. Okay, go ahead.
الحال؟
मिनाहिल नाम की इब्तदाई तारीख हिंदी जुबान
Okay, I'm going to take a stab at this again. Minahel, did I get that right this time or no? Was it bad? Was it real bad?
It's not real bad. It's fine.
No, I want to get it right. I want to say it like your mama said it. So, again?
It's Minahil.
Minahil. Dang it. I debated between each A. I remembered it was an A. See, a little bit each time. I will get it eventually, even if I have to ask you like 10,000 times. I'm so sorry. Okay, Minahil. Say it again. All right. Talk me through what you guys did.
So first we kind of just did the number of electrons that it would be. So it was like 32.
Okay, so what molecule is it? How do I write it?
CCl4.
Okay. And then what next?
So then it was like hold on, I need my reference packet again. Okay, so C had 4 valence electrons, and then Cl has 7, and then there's 4 Cl, so that was like 32 in total.
Yeah, because there's 8 sets of 4, so there's 32 valence electrons. So what do I do now?
And then put the C in the middle.
Okay.
And then connected it to 4 Cls with like the line.
Yeah, with the single bond. All right.
Yeah. And then just put like the other 6 valence electrons on each chloride.
Good. All right. So when we check it, we can see that there's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. We are good to go. Now, is this polar or non-polar?
It's non-polar.
How do you know it's non-polar?
Because it's all balanced.
It's all balanced. It's symmetrical in shape, and they're all bonded to the same thing. So if it's non-polar, what does it dissolve in?
Oil.
Oil. Now, just to make a point, you're good. Minahil, I got it. All right. So when you do these dipoles do exist, but they are equal and opposite. This is a 4-way tug of war between the Hulk and himself 3 other times. So even though they're both pulling on this direction, they balance each other out. So you take 1 step forward, 1 step back. Same thing. You add these arrows together, or vector addition if you like physics. 1 step forward, 1 step back. Then you end up with a completely balanced molecule. Okay. Last, we have particle diagram. So we're going to do what we just did. We're going to include the partial positive and partial negative charges, meaning we know that these are polar. And the only thing we're adding is a water molecule. So if I go back here and I see this polar molecule, I know that water looks like this. Which side is more negative? Which atom in that is more negative? Magana, which one? In the water molecule, which one's more negative?
I'm not sure.
Okay, so which one is closer to fluorine?
Oxygen?
So whichever one's closer to fluorine is more electronegative because fluorine, the floozy, right? She'll do anything, get her electron. She's desperate. So all of her mean girls in the corner are also desperate. So oxygen is going to hog the electrons. So is he going to be more positive or more negative?
More negative.
And hydrogens are going to be more positive. So here's my question. Which of these two, this nitrogen or this fluorine, is going to be more attracted to the oxygen?
The nitrogen?
Yes, because opposites attract. So if I were going to draw a particle diagram, I would draw this molecule and I would draw water with oxygen facing the nitrogen, right? Because this is partially negative and that's partially positive. Okay, so this is what it would look like. If I were going to draw near the fluorine, I would draw the hydrogens near the fluorines because they're partially positive and the fluorines are partially negative. Okay, so that's what I'm asking you to do here. Oop, 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 oop. No. Dang it. I have to start over again. Hold on. I hate when I do that. Ha, here we go. All right. You're going to do the exact same thing we just did for ASF and NH3, but I want you guys to do them with the water molecule. So it says draw at least one molecule. Again, this is the end of 7.2. This is the last thing we're doing today. I'm going to do ASF3 as an example, then you guys are going to do NH3, okay? So AS, just using the concepts that we've already learned, AS is arsenic. It is in group 5, and therefore it has 5 valence electrons. So I have 5 plus the 3 times the 7 fluorine has from group 17. So this is a 26 valence electron molecule, which we have seen already. The AS goes in the center because it's first. I'm going to draw the fluorines around the outside. They have to be single bonded. I'm going to add my 6 electrons per fluorine. And 2 on the arsenic, okay? So now I know it's going to be polar because I said assign the partial positive and negative charges. So the negative charge is going to be the most polar atom of the unequal or unbalanced pair. So this fluorine and this fluorine are evenly matched. They are not going to be related to my polarity. But this fluorine and this lone pair are not equal. This is going to be partially negative because it's stronger. This is going to end up being partially positive because arsenic is weaker and there's no bonded atom here. So it's asymmetrical in shape. Okay. When I add the water molecule, the oxygen is going to be closest to arsenic because it is partially negative and these are partially positive, and I'm going to have my 2 lone pairs on that oxygen. My hydrogens are going to be close to the fluorine because they are partially positive and this is partially negative. So this is the process I am asking you to do, okay? Draw your molecule, assign the partial charges, and then make the water, 2 water molecules, what it looks like near the positive side. I should do this so it matches the arsenic. The positive side and the negative side. So this is partially negative. And then these partial positives go with that hydrogen, okay? So I'm gonna put you in breakout rooms. Oop, oop, go back. You're gonna do the same thing for ammonium. And we've already done a couple of these. That's why I went through the example. You have 5 minutes, okay? 5 minutes to do ammonia. Go back to your room. This is the last thing we're doing today. 5 minutes.
Well, I can try.
Okay, awesome. Walk me through it.
So I started off by saying that nitrogen was in group 15, so it has 5 valence electrons, and there's only one nitrogen, so it's only 5 valence electrons. And then hydrogen is in group 1, so there's 1 valence electron, and it's 3 hydrogens. 3 times 1 is 3. So that's a total of 8 valence electrons. And then for the molecule, since well, hydrogen can never be in the middle, right? So it has to be
Right, because it can only make one bond.
right. So it's the N goes in the middle, and then 3 H's around the N, and then 3 bonds from each end. So that's and then 1 lone pair on the end. So that makes 8 valence electrons.
Now, what did you decide for your partial charges?
I said that the nitrogen is more electronegative than hydrogen. So I said each of the hydrogens were partial positive, and the nitrogen was partial negative because it has a lone pair on it. And it's the whole electrons.
How would water go?
Water, so water, I did the O in the middle, oxygen 6 valence electrons, hydrogen is 2 times 1 is 2, that's 8. So I did the O in the middle and then 2 H's on the side. And then
Right, where would that O be close to? Or the oxygen?
the oxygen is partial negative, so that would be farthest away from the nitrogen, and the hydrogen would go closer to the nitrogen.
Yep. So drawing both options there. Okay, great job. All right, guys, that is everything we were doing today. You have covered 7.1 and 7.2 material. We finished up 7.1, covered 7.2. You should be getting confident. You should be having practice. You should be more confident than you were. But that is the end of class. So if you have any questions, let me know. But if not, you are free to go. Okay?
So just to clarify that when doing calculations, and we have like the 1 mole to 22.4 liters, etc., we should always take those as exact measurements in this class.
Yes,
right?
conversions are exact numbers.
Okay, thank you. Have a good day.
So Miss Longley, the QC 7.2 isn't due until next Tuesday.
No, it's not due until 2 classes from now, but like, it's because we delayed the grading of 7.1 and then we didn't want to pile you with 3 QCs in one day. So 7.2 and 7.3 are 2 classes from now for the end of the week.
Okay, gotcha. Thank you.
No problem.
And then 7.1 was over the stoichiochemistry.
Yep,
right?
stoichiometry. So 7.1 is oh, come on, this, not that. It's over this question, basically. This one we did. And we're not letting me go back and forth, but here we go.
Oh, okay.
That one.
Oh, okay. Thank you.
Yeah, no problem.